So what is the difference between these two feature control frames? First, we have a perpendicularity of 20 thousandths to datum A, and then we have a total runout of 20 thousandths to datum A. Now, make it clear, we can't use both at the same time. We're going to pick one. Datum A, shown right here, is the axis of this large diameter. The surface we're controlling is 90 degrees to that axis. Now, this is an implied 90-degree angle. If there was no Gd&t, it would revert to your title block plus or minus half a degree or 1 degree or whatever. But since there is Gd&t control on it in either of these ways, we get a basic 90-degree angle from the datum axis. Now, let's talk about it in terms of tolerant zones. With perpendicularity, right, we know our tolerant zone is two parallel planes that are perpendicular to our datum axis or a datum plane or whatever our primary datum reference is. So that's going to look something like this. Now, what's a little trickier to draw is those planes that are perpendicular to A are free to move left and right. They're only oriented to A. They can't be located to anything else because it is an orientation tolerance. So the actual location of that surface comes from here. So if this comes in at maximum material condition 1.02, we can't have any variation outward, right? It could only go inward. If it's in the middle of the tolerance zone, right? You could use this whole thing. And that's very important, right? Orientation cannot control location. If this is basic, now we have a problem, right? Now there is nothing controlling the location of this surface. A lot of times this is not a problem because we'll have an unless otherwise specified profile. We would need a datum B, right? Because if we're going to locate this surface, it's got to be located left and right relative to something. It can't be A, it can only be oriented to A. So we need to make up a datum B. Now, I'm not saying one way is necessarily better than the other. I've seen plenty of turned parts that use plus or minus dimensions for everything except, the actual cylinder, so all the left-right dimensions. Okay, that's perpendicularity. What about total runout? The same thing about location applies with total runout, right? Runout can never control the location of something because the classic example, and I know this is not shown in Y145-2018, the classic example is you put your indicator, zero it, and then spin the part 360, right? If you can zero your indicator on the part, you're not measuring location. Measuring location would mean you zero it at datum B or somewhere else, and then you come back out a specified distance, right? And then any variation on your indicator would tell you the location. So runout, in the classic form, does not control location. So here, this works just fine. We have a profile controlling the location. Runout is going to be controlling the form. Now, the old definition for runout was an indicator, right, 90 degrees to the surface, if it's surface perpendicular to the datum axis. Spin it 360, move the indicator down, right? It can only be zeroed once. Spin it, move it down, spin it, move it down, spin it, as opposed to circular runout, where you can set your indicator, spin it, take your indicator away, put it back, right? And you can get a surface that's a little bit more wavy. Circular runout does not control flatness. So, in my opinion, these mean the same thing. There is no difference. It should not affect inspection. In Y145-2018, I think they've made it very clear. They've taken out references to dial indicators, right? I think there used to be kind of a thing like, oh, well, in Y145, it shows an indicator measuring runout in 2009 and before, so we have to use an indicator. That was never true, but now they've taken all the helpful pictures out, and it's just a description of the tolerance zone. So that is perpendicularity and total runout. What about circular runout? Right, well, we're here. So circular runout is an odd duck. It controls wobble, right? So if we set our indicator here and spin it 360, As long as we stay on this kind of crest, we're good, right? Then we can take the indicator away, re-zero it in this trough. So you can end up with a part, it kind of looks like this, right? Very odd. What's going to limit the distance between the crest and the trough is either your plus or minus dimension, if we have one, or whatever is controlling the location, right? So in that way, it doesn't control flatness, and it doesn't really control orientation. I guess you could say it maybe controls tangent plane orientation. I don't know. I don't want to get into it, but it's a very odd thing, and definitely not the same as a perpendicularity call out. We could also just use profile, right? So here is a more direct way of showing it. Profile 40 thousandths to A and B. Right? That B is translation left and right. That's your location. This lower profile is only to A. It can only control orientation and form. That's going to do the same thing perpendicularity or total runout did, except now we've got it kind of all in one package. And in this case, composite profile and two single segment mean the same thing. So that's it for this video. If you enjoyed it, please like and subscribe, and leave a comment down below.